This video is on section 2.7, the derivative as a function. So up until now, besides the very last example in 2.6, a was always a specific value that we were focused on finding the slope of a tangent line, to a very specific point. But as we did in the last example of 2.6, it makes total sense and there's a lot of value in finding the derivative as an equation, as a function, in which we can then find the slope of a tangent line to any point to the specific function. So consider we know now the definition of the derivative is the limit as h approaches 0 of a step from some value a minus the function evaluated at the value a all over h. But what if we take out the specific value of a and replace it with just a function of x? So if we are looking at the graph of f, use it to sketch the derivative of f of prime. Okay, well, recall that the derivative represents the slope of the tangent line. So if we are looking at the slope of the tangent line at every single point, we can then denote what the graph of the derivative would be. So let's first start with where is the graph of the derivative equal to 0, meaning intersecting the x-axis. And that would be whenever the tangent line has a slope of 0, which would mean a horizontal line. So notice that every min and max, whether local or global, is where you would find a slope being equal to 0. So I know that the points at which the derivative crosses the x-axis or is equal to 0 is at A, which looks like about 0.5, B, which looks like maybe 1.5, and C, which is at the x value of 3. So notice that when I draw the derivative, I make sure to cross the x-axis at those 3 points. When it comes to the rest, this has to do with the derivative is increasing because the original function is above the x-axis for this whole time here. So notice that we're going to be increasing. Okay, I think I said that backwards. Notice that the original function is decreasing from negative infinity to a. So because it's decreasing there, the derivative is below the x-axis. I definitely said that backwards. The derivative is above the x-axis between a and b, which translates that the original function should be increasing. Just note that the derivative is negative when the original function is decreasing, negative sloped line, and the derivative is positive above the x-axis for positively sloped lines. So for between b and c, we are fully decreasing on the function, so we would expect the derivative to be below the x-axis between b and c, and we see that. Now looking at the derivative, after c, we see that the entire derivative is above the x-axis, so our expectation is that it should be increasing in the original function, and that is true. Now, where did we get these pretty curves from, and how do we know how far up or how far down to draw? That we haven't learned yet, so if you're confused about that, don't be. We will learn that in a future section. Let's find the derivative of function x squared using the limit definition. Now, if you know what the shortcut rules are, great, that's great to check your answer, but up until the first exam, the expectation is you will do the limit definition out, and shortcuts will receive 0 credit. If you have no idea what I'm talking about, then you have nothing to worry. But for those of you who have taken calculus before and have learned how to do derivatives without using the limit definition, that is not sufficient to get full credit from now to the first exam. After the first exam, we will learn all the shortcuts and we will never have to do the limit definition again. So let me do this problem on the whiteboard. So we're looking at the function x squared, and we want to calculate the formula for the derivative. for any point on this parabola to draw a tangent line through. So we're going to want to use the limit definition that states the limit as h approaches 0 of f of x plus h minus f of x all over h. And we are solving this in order to find the equation of the derivative that gives us the slope of the tangent line at any point. So I'm going to find the derivative by doing the limit as h approaches 0. Now, this tells me replace x plus h in for every x in the f of x function. So I'm going to have x plus h squared minus just plain old f of x, which is x squared, all over h. Again, we have to do x plus h times x plus h. And since this is the same calculation you'll do several times, it's okay to not show me this foiling algebra work, as it's going to be the same every time, and it's okay to assume that. So now I'm going to write the limit as h approaches 0, replace my x plus h squared with x squared plus 2xh plus h squared minus x squared all over h. My x squared terms cancel, and no surprise, I'm left with only terms with h in it, allowing me to factor my numerator, and specifically factoring out an h so I can cancel it with the h in the denominator, eliminating my problem with dividing by 0. Now, as I let h go to 0, this term turns to 0, leaving me with the formula 2x. Now, if I wanted to find the slope of the tangent line to any point on x squared, I would take the x value of the point and put it into 2x, my formula for the slope of the tangent line, and I would be able to find the slope that quickly. Let's see what our next example is. So the next one we want to try is finding the derivative using the limit definition of the derivative to find the equation of the tangent line. So now we're going to go farther and find the equation of the tangent line to the cubic function negative x cubed at the point x equals 1. Back to our whiteboard. So again, we're using the function negative x cubed, and we're trying to find the slope of the tangent line at x equals 1. But first, let's practice the definition without knowing the 1. So we're going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. So we have the limit as h approaches 0 of negative x plus h cubed. I replace the x plus h with, I replace the x with x plus h minus a negative x cubed. Careful of that one. I almost didn't do the double negative. The negative is part of the formula, and this negative is part of the equation. Let's do our math. We know that x plus h times x plus h is x squared plus 2xh plus h squared from the last problem. But because this is cubed, we need to multiply it one more. And if you know Pascal's triangle, then you already know what the coefficients are for this particular answer. But if you don't, keep note of what they are, as they're not going to change. So we distribute through the x, so we get x cubed plus 2x squared h plus xh squared. Then distribute through the h, so we get x squared h plus 2xh squared plus h cubed. We then combine like terms. So I have an x squared h here with 2x squared h is there. I have an xh squared with 2xh squared there, giving me x cubed plus 3x squared h plus 3xh squared plus h cubed for that x plus h cubed part. So we have the limit as h approaches 0 of negative x cubed plus 3x squared h plus 3xh squared plus h cubed minus a negative x cubed, giving us plus x cubed all over h. We now need to distribute this negative sign all the way through and then hopefully be canceling all x terms. So we have the limit as h approaches 0 of negative x cubed minus 3x squared h minus 3xh squared minus h cubed plus x cubed all over h. Our negative x cubed and our positive x cubed cancel, leaving us with all terms with h in it, and we are able to factor out an h in the numerator, leaving us with negative 3x squared minus 3xh minus h squared all over h. Our h's cancel. Our terms with h in it go to 0 as we take the limit, leaving us with an equation negative 3x squared as the formula to use in order to find the slope of any tangent line to the function negative x cubed. And we want to find the slope at x equals 1. So that would give us negative 3 times 1 squared, which gives us negative 3 is the slope of the tangent line at x equals 1. In order to complete the problem, I need the y value that corresponds to 1. And in order to do that, we need to go back to the original function in negative x cubed in order to find what is the y value, and it is negative 1. So we know this is the point 1, negative 1. Using our point slope form, y equals negative 3 is the slope times x minus 1 plus a negative 1, which is our y value. Do out our algebra so that we have prettier looking function here. And we get y equals negative 3x plus 2 is the slope, or is the actual equation of the tangent line to the function negative x cubed at x equals 1. All right, let's head back to the PowerPoint now. So other notations for a derivative you should be aware of. The tick mark is very common, and it can be done with a function notation f prime of x, or in just regular y notation, y prime. You'll also see the following notations for the derivative. dy dx tells you that the dependent variable is y and the independent variable is x. You're taking the derivative of the y function with respect to the variable x. Same thing is here, except you're using function notations. You're taking the derivative of the function f with respect to the independent variable x. And these are all different types. These notations here, the last three, are less likely to see in calculus. You see these in differential equations more, and I would say we work with the first couple the most in this class. How can a function fail to be differentiable? Whenever we have a point in the function where the tangent line is a vertical line, which we know that the slope of vertical lines are undefined, that's when the function is not differentiable at that point. So in the case of the absolute value function at 0, the derivative does not exist. And that's because the slope of that tangent line is undefined as it creates a vertical line. Okay, so any place in a function where the tangent line is a vertical line, it is not differentiable at that value a. Okay, and this concludes our 2.7 lecture.